Welcome to the second part of Lecture 13, the definition of the curl. It's entitled Curl Around a Path and Relate It to its Area. Okay, now we're going to work on defining the curl. It's defined analogously to the way that we define the divergence. However, this time what we're doing is we're looking at a line integral and comparing it to the area versus a surface integral compared to the volume. So we start with a small rectangle, which is shown for you on the left-hand side. We're going to integrate the circulation of the vector field F around the boundary and then divide by the area. So the integral around the boundary is just the line integral given by the integral around the whole boundary of f dot t ds, and we can break it up into the four different components, integrating along the top, the left, the bottom, and the right. Now, when we carefully look at this, so let's take a look at the top, you can see the tangent vector is pointing in the minus x direction, so it's equal to minus I hat. And if the center of that rectangle is this point xyz, then this point is going to be xyz plus dy over 2, where the y is increased by dy over 2, and it has a minus sign in front of it. And so if I work that out for all of the different components, you find I get these four different terms. So when I look at the left-hand side, it's minus fy evaluated at x minus dx over 2, and the integral along the bottom is fx evaluated at y minus dy over 2, and finally the integral along the y direction, along the right direction, the right leg is fy valued at x plus dx over 2. And then depending upon whether my line is going along the horizontal direction, I multiply it by a dx for the integral along there, or I multiply it by a dy if it's in the vertical direction. Okay, good. I can sum all of those together and use the definition of the derivative. In particular, let's focus on the fx terms. You see there's an fx of x y minus dy over 2 minus an fx of x y plus dy over 2. That clearly is minus the derivative of fx with respect to y. And indeed, that's the term that appears when we put this together, and that would be multiplied by dy. So that's where the extra factor of dy comes out. And you can see that I've got leading in front of this an area. So if I ultimately divide by the area, I'm going to just be left with the derivative terms. Similarly, if we work in the yz and the zx planes, we'll find dy dx df z dy minus dfy dz, or dz dx dfx dz minus dfz dx. And so you should carefully work out and make sure you understand where all of those terms come out, and understand carefully how I got the signs right in doing those particular calculations. All right, we're almost there. Now, the area enclosed for each of those rectangles is dx dy, dy dz, or dz dx. We're going to be dividing by that area. And the only subtlety here is the final object that we're going to call the curl is actually a vector. And each of those objects that we calculated for each of the three different rectangles are actually components in three different directions. We determine what the direction is by curling our fingers in the direction of the integral, and then our thumb points in the direction of the loop. So if we look at the red box there, which is sitting in the YZ plane, if I curl the fingers of my right hand in the direction of that circulation, my thumb points out of the board or out of the page, and that is in the positive x direction, so it's equal to a unit vector called I hat. And you can similarly work out what it is for the xz plane and for the xy plane, and that's the unit vector that we're going to multiply each of those scalar values by and add them up to get the total vector, because as mentioned before, the curl is a vector, and so we have to have a way of converting from those scalar values to the vectors. So after all the dust settles from doing this, we get our final answer. And there are three components to it. There's one in the x direction, one in the y direction, one in the z direction. And it's each of those different combinations of derivatives that have minus signs in them. And you're probably familiar with this. You've probably seen curl before. In fact, during the problems on the last lecture, we actually worked with the third object, the one proportional to k hat. in the last part of the equation. Now, we take the limit as the area and the rectangles get smaller and smaller, and in the limit where the rectangles go to 0, we call that answer the curl of f. Sometimes it's called del cross f. And then we often write it in this determinantal form, where we put the 3 unit vectors in a column on the left-hand side, we put the 3 differential operators in a column in the middle, and we put the 3 components of the vector field f on the right-hand side. And then as you work through the pieces, so for example, we draw a line to calculate the first term, that would be a dfz by dy multiplied by an I hat. And you see that has a positive sign. And then the second term that's multiplied by I hat we get by looking at the matrix in this form, and that would be a dfy by dz multiplied by a minus sign and also multiplied by I hat. And then you could similarly work out the other 3 versions of the curl to get the other components of it. So I hope that this lecture has explained for you what the definition of the curl is, and I hope that you can understand and now use this as we move on from the definition of curl into the integral theorems. In particular, this is going to be Stokes theorem that we're going to be looking at as we look at macroscopic line integrals around closed curves and comparing that to integrals over the area or over the surface that those paths enclose.